In today's class and video, we are going to look at the determination of maize germ acid phosphatase pH optimum, or the optimum pH for our enzyme acid phosphatase. So first of all, what we have to note is that enzymes are basically affected by changes in pH. And also the most favorable pH value, or the pH where the enzyme is most active, is known as the optimum pH. So from this graph over here, we can see that this is a graph showing the optimum pH for two enzymes. So this is the first enzyme and this is the second enzyme. So the first graph is showing the optimum pH for pepsin, which happens to be a stomach enzyme. And from the graph, we can see that the optimum pH for this enzyme is around 1.9 to 2.0. And the optimum pH for the trypsin, so which also happens to be an intestinal enzyme, is at the pH of 8.0. So let's start our test protocols, and first by looking at the materials that we are going to use for this experiment. The first is 0.15 molar EDTA in 0.01 citric acid buffers of different pH values as shown over here. So we also have our artificial substrate, which is 2.5 millimolar p-nitrophenol phosphate at pH 4.3. We also have our acid phosphatase as our enzyme. We have our 0.1 molar sodium hydroxide. We also have our spectrophotometer set to a wavelength of 405 nanometer and our water bath set to a temperature of 37 degrees Celsius. So let's start our test method. So the first is the preparation of our substrate buffer. And to prepare our substrate buffer, which happens to be our EDTA citrate buffer and our 2.5 millimolar NPP as the artificial substrate, we are going to use the table over here to do that. So we can see that the table contains our test tubes, 8 test tubes, labeled as 1, 2, 3, 4, 5, 6, 7, and 8. And it also contains an amount of EDTA in mils and a volume of our artificial substrate in mils. So now let us take the test tube one by one and look at how to prepare each substrate buffer. So for test tube 1, we have 2 mils of our EDTA citrate buffer and 2 at a pH of 3.0 and 2 mils of our 2.5 millimolar NPP. For test tube 2, we have 2 ml of our buffer at pH 4.0 and 2 ml of our artificial substrate. For test tube 3, we have 2 ml of our buffer at pH 4.5 and 2 ml of our 2.5 millimolar NPP. For test tube 3, we have 2 ml of our EDTA citrate buffer of pH 4.5 and 2 ml of our 2.5 millimolar NPP. For test tube 4, we have 2 ml of our buffer of pH 5.0 and 2 ml of our 2.5 millimolar NPP. For test tube 5, we have 2 ml of our buffer at pH 5.5 and 2 ml of our 2.5 millimolar NPP. For test tube 6, we have 2 ml of our buffer of pH 6.0 and 2 ml of our 2.5 millimolar NPP. For test tube 7, we have 2 ml of our buffer and 2 ml of our 2.5 millimolar NPP. And for test tube 8, we have 2 ml of our buffer at pH 8.0 and 2 ml of our 2.5 millimolar NPP. So the combination of the EDTA citrate buffer and our artificial substrate forms our substrate buffer. So the next protocol is the dilution of our enzyme. And to do this, we dilute our stock acid phosphatase solution with distilled water in 1 in 10 dilution. And to do this, we pick 1 ml of our stock acid phosphatase and add to 9 ml of distilled water. So the next is the equilibration of our substrate buffers and our diluted enzyme. So to do this, we equilibrate the substrate buffers and the enzyme at 37 degrees Celsius in a water bath for 5 minutes. And what we also have to note is that the substrate buffer here represents the other substrate buffers prepared. So whatever is being done to this substrate buffer in this experiment, the same must be done to the rest of the substrate buffers in the other test tubes. So now let's see how to perform and stop our reaction mixture. And we are going to do this at 0 time or 0 minutes and at 30 minutes after we prepare our reaction mixture. So let's start by looking at 0 time or 0 minutes. So we add 1 ml of the diluted enzyme. So this is the diluted enzyme, so which has been equilibrated, to our test tube labeled as 8. And once we add our equilibrated enzyme to this test tube, we now begin with our reaction mixture. So the next thing to do is that we mix, and immediately after adding the 1 ml of the equilibrated enzyme to this test tube, we pick 0.5 ml of the reaction mixture and add to a different tube containing 5.5 ml of 0.1 molar sodium hydroxide, and this stops the reaction. So after that, we used this stopped reaction over here at 0 minutes as a blank against the rest of the reaction mixtures at a wavelength of 405 nanometer. So we then allow the reaction mixture in the water bath to cool and measure the pH. So what we can also see from this diagram over here is that after we remove the reaction mixture from the water bath, the volume, which is initially 5.0, will be reduced to 4.5 ml because 0.5 ml of this was picked and added to a test tube containing 5.5 ml of our sodium hydroxide. So let's see what also happens at 30 minutes. So for 30 minutes, we add 1 ml of the equilibrated enzyme to the remaining test tubes and incubate for exactly 30 minutes. And what we also have to note is that once we add the equilibrated enzyme to our substrate buffer, then that means it now becomes our reaction mixture that we need to incubate at 30 minutes at 37 degrees Celsius. So once we are done with this, we pick, after the 30 minutes of incubation, we pick 0.5 ml of the incubated reaction mixture and add to a different test tube containing 5.5 ml of 0.1 molar sodium hydroxide to stop the reaction. And what we also have to note is that the test tube in this water bath represents the remaining test tubes containing the reaction mixtures at different pH. So once we stopped the reaction at 30 minutes by pipetting 0.5 ml of the reaction mixture and adding it to the 5.5 mils of our 0.1 molar sodium hydroxide, we measure the absorbance at 405 against the blank prepared at 0 minutes. So once we are done, we remove the reaction mixture from the water bath and allow it to cool and measure the pH. And also over here, this reaction mixture represents the remaining reaction mixtures in the various test tubes with different pH. So whatever is being done to this reaction mixture over here should be done to the other test tubes containing the reaction mixtures. So now let's see the assumed table of results. So we did 1 in 10 dilution. So this is a table showing the pH values and the measured pH with the pH meter and the obtained absorbance value. So from the table we can see that at pH of 3 we had the measured pH was 11.98, and this is as a result of the presence of the 5.5 mil sodium hydroxide, and the absorbance value is 0.361. So at pH 4.0, this happens to be our pH, our measured pH, and this is our absorbance. At pH 4.5, we had this as our measured pH and the measured absorbance value. At pH 5.5, we had this as our measured pH, and this is also the measured absorbance value. At pH 5.5, we had this as our measured pH value and the measured absorbance value. At pH of 6, we had the measured pH value to be 12.29 and that of the absorbance to be this. And also at pH 7.0, we had the measured pH value to be this and the absorbance value to be this. And also at the pH of 8, we had our measured pH to be 12.4 and the absorbance value to be 0.0 because we used the test tube with the pH of 0 as our blank against the rest of the pH values in the different test tubes. So obviously the absorbance value for the pH of 8 will be 0. Now let us now look at how we will determine the moles of p-nitrophenol hydrolyzed by our enzyme acid phosphatase in our reaction from the calibration curve. So first of all, this is a calibration curve that we plotted in our previous videos and class using our 60 micromolar p nitrophenol. So this is the calibration curve over here. So from the calibration curve, we can see that we plotted the absorbance values at this wavelength against the moles of p nitrophenol, and this is also our equation of the line, which is giving us y equals 6.7318 s. So where the y happens to be the absorbance value, the 6.7318 happens to be our slope, and the s happens to be the moles of p-nitrophenol hydrolyzed. So first of all, what you have to note is that if you want to determine or extrapolate the moles of p-nitrophenol hydrolyzed from the calibration curve, we make S the subject from the equation of the line. So if you are to make S the subject over here, we will get H to be equal to y divided by the slope, which is 6.7318 over here. And to be able to extrapolate or determine the moles of p-nitrophenol hydrolyzed, we substitute the absorbance value from our test at the 30 minutes in the place of y and calculate the value for the S. So the calculated value for the S happens to be the moles of p-nitrophenol that was hydrolyzed from our reaction at our 30 minutes. So if you are to do that by making X the subject and substituting Y with the absorbance values over here, then we can say that at pH of 3.0, the moles of p-nitrophenol hydrolyzed from the calibration curve will be 0.054, and that of the pH 4.0 will be this, and that of the pH 4.5 will be this, and that of the pH 5.0 will be this, and that of the pH 5.5 will be this, and that of the pH 6.0 will be this, and that of the pH 7.0 will be 0.052, and obviously the moles of p-nitrophenol hydrolyzed at pH 8.0 will be 0 because we used it as our blank against the rest of the pH values. So now let's see how to calculate our acid phosphatase activity. So first of all, what we have to notice is that when we talk of enzyme activity, it's just the moles of substrate hydrolyzed by our enzyme per unit time. And for our incubation, we did our incubation for 30 minutes, and the 30 minutes is the same as 0.5 hours. So if you have to convert the 30 minutes into hours, it's the same as 0.5 hours over here. So let's see the phosphatase activity for our enzyme acid phosphatase, which is giving us the moles of p-nitrophenol hydrolyzed or formed per our 0.5 hours over here. So to do this, we divide the moles of p-nitrophenol formed or hydrolyzed by our 0.5 hours over here. So upon doing that, this will be the phosphatase activity values that we are going to get, and this table of result is just showing us the pH and the absorbance and the moles of p-nitrophenol formed from the calibration curve and the calculated phosphatase activity. So if you should look at this table, we have at pH of 3, we had our phosphatase activity to be 0.108. At pH of 4, we have 0.140. At pH of 4.5, we have 0.166. At pH of 5.0, we had 0.20. At pH of 5.5, we have 0.246. At pH of 6.0, we have 0.180. And at pH of 7, we have 0.104. And obviously at pH of 8.0, there will be no moles of p-nitrophenol hydrolyzed because we used it as a blank against the rest of the test tube. So we are to plot the optimum pH for our maize germ acid phosphatase, and to do this, we plot our phosphatase activity or the enzyme activity in micromoles per hour against the pH over here. So if you are to do this, this will be the nature of graph that we will get over here. And from the graph, we can see that the optimum pH for our maize germ acid phosphatase is 5.5. Thank you.